Wonderful. So without further ado, we'll get going today. I'm very excited to see everyone here, and good morning and good afternoon, depending on where you are. We're so happy you could join us today for this first live session. We're very appreciative to have Dr. Christina McGraw joining us today to review some of the concepts and answer your questions from this module. Hopefully by now you've had a chance to watch your excellent lectures, take a look at the reading, and test your knowledge with the quiz. Thank you to those of you who have contributed to the discussion forum as well. Dr. McGraw will be covering some of those questions from that today too. But before we dive in, I wanted to take a moment and welcome you to the course, since this is the first time we're joining together. We're so glad to see the interest in this topic, and we're very glad that you could join us, so thank you. Putting this course together has been a large group effort. The staff at the IOC's Ocean Teacher Global Academy has been key to creating the course platform, designing the content of the modules, and making sure everyone's been able to register. And the specific use of this course has been enabled through a joint effort by the Ocean Foundation, the National Oceanic and Atmospheric Administration, and its Ocean Acidification program in the US, the Pacific Community, University of the South Pacific, University of Otago, and the National Institute of Water and Atmospheric Research in New Zealand, and the Pacific Islands Ocean Acidification Center, which you'll hear more about in our live session next week. We've also benefited from expertise from the Intergovernmental Oceanographic Commission of UNESCO, University of Hawaii, and a number of other global experts, as well as the support of the US Department of State and NOAA. So I'll take a minute to introduce some of us that are working on the back end, who you'll see in the discussion forum and in future live sessions, put a face to the name. I'm Caitlin Lauder. I'm a Senior Program Associate at the Ocean Foundation. I work on our International Ocean Acidification Initiative, which includes efforts like this to build capacity for OA monitoring around the globe. I came to the ocean acidification field about 10 years ago, and I studied the effects of ocean acidification and warming on crustacean predator defenses, particularly those in spiny lobster. So I have some experience running biological experiments and doing water chemistry measurements in the lab, which I'd be happy to talk with any of you more about. But for now, I'll turn it over to some of our other hosts. We'll start off with Alexis.
Thank you so much, Caitlin. My name is Alexis Filari Orton, and I am also at the Ocean Foundation, where I manage our International Ocean Acidification Initiative. This is really, really exciting for me because this is the largest training we've been able to do using this online platform. I have been working on ocean acidification for most of my career and had the opportunity to study ocean acidification actually in the Cook Islands about 10 years ago. So I have a little bit of experience living and working in the Pacific. Thanks, Caitlin.
Thanks, Alexis. I'll turn it over to Alyssa next.
Hi, everyone. My name is Alyssa Hilt. I also work at the Ocean Foundation, and I help with supporting our ocean acidification initiative. So you'll see me around behind the scenes on Zoom, Q&As, helping to answer questions and keep things rolling behind the background. And you'll also see me around in the discussion boards, commenting here and there and interacting with you all.
Wonderful. Thanks, Alyssa. Over to Meredith.
Hello, my name is Meredith. I'm being told that I can't turn my video on, if it's possible to click the switch so I can show people my face.
1 minute, we'll get that.
Here we go. Thank you, Caitlin. My name is Meredith Kurz. I'm at NOAA's International Activities Office within the NOAA Research Branch, and it's my responsibility to develop and maintain our partnerships with the Pacific partners that we have across the Indian Ocean and through the Pacific Basin. And I also support some of our specific programs with executing their activities with international partners. And my favorite one to help support is the NOAA Ocean Acidification Program. And so I'm so happy to be here. I'm so happy to see so many people joining us to learn more. Thank you. Over to you.
Thanks, Meredith. I'll pass it over to Alex.
Hi, everybody. My name is Alex. I'm with the NOAA Ocean Acidification Program, and I work on our competitive portfolio of external funding opportunities, and excited to be here tonight. I'll be helping to field questions in the chat box. Thanks.
Thank you. And next, Gabby.
Hi everyone, I'm Gabby Kitch. I'm also with NOAA Ocean Acidification Program. I'll be monitoring the Q&A and the chat tonight. You'll also see me popping in and out of the discussion board on the OTGA platform. So it's really good to meet you all.
Thank you so much. So that's just some of our team that's been working on this course behind the scenes, and we're glad to meet you today. Just as a reminder, feel free to add your questions into the Q&A box. I believe you can upvote each other's as well if someone has a similar question. Without further ado, I'll turn it over to Dr. Christina McGraw, who has not only been the lecturer for Module 1 and created this wonderful introduction to oceanification, but has been so helpful in terms of getting this course up and running. So thank you so much.
Great, thank you, Caitlin. Let me just share my screen.
Looks great.
Great, all right. Well, thank you everyone for coming today. And I guess kia ora koutou. Thank you for joining us. And today is going to be a little bit of an overview. So the fact that you're here today kind of tells me that you've already watched all of the other lectures. So today we'll be discussing a little bit more just general information. So some of it will be a little bit of a review of what we talked about, but hoping to go a little bit deeper in some of those areas that you guys said were the most interesting when you were answering Caitlin's feedback in the discussion board. Also, we've had some really great questions, so kind of sprinkled throughout today, I will address them. And if we don't get to your question, definitely just keep putting it in the discussion board and we will make sure to get to it. Now, Caitlin kind of alluded to an extra workshop, and I think you've maybe been told about it in the email, but next Wednesday, we are going to have a separate workshop that is really specific about resources and opportunities for the Pacific region. So I'll talk more about that at the end of today, but just keep that in mind, please, as we're going. So for today, just I suppose to start with a little bit of an introduction. So my name is Christina McGraw. I am here at the University of Otago, which is in New Zealand. And I've shown this beautiful map that Caitlin made, which just shows the location of a lot of the participants. And what you'll see is that you can't actually get probably much further south or much colder than here in Dunedin. So it's beautiful and sunny, but also often a little bit chilly because there's not much between us and Antarctica. But it is a beautiful place to study the ocean. We're in a harbor and we've got a lot of great rocky shores, sandy beaches. We have one of the most rare penguins in the world if you are a birder. So it's a great place to come and visit and kind of explore the marine environment. Myself, I'm a marine analytical chemist. I build scientific instruments to help understand the changing marine environment, mostly involving ocean acidification. Now, this involves building everything from really small sensors. One of my favorite ones my lab's working on, it's about the size of a sewing needle, but it looks like a tiny glowing lightsaber. And it helps us measure ocean acidification parameters, such as saturation state, in real time. I also build really big things like room-sized culture systems that let researchers like botanists grow organism under future conditions. So they can change things like pH, oxygen, nutrients, light, and temperature in up to 50 culture tanks. I also do a lot of work with experimental design. And so this is going to come up a little bit later, not through me exactly, but I work with people like Sam DuPont on it, and he's going to talk about metal resources later. I know a lot of you are here because you're interested in monitoring, but also a lot of people are interested in doing experiments. So check out some of those experimental design resources as you go through. Now, the last thing I do want to say about Dunedin is that it is the home of the Munida Time Series. So the University of Otago, it's actually run by NIWA, or the National Institute of Water and Atmosphere. It is the longest running ocean acidification time series in the Southern Hemisphere. It's been going for about 23 years now. So it's really a great set of data to understand what's happening to the pH in our region. And that's all widely available. So if you just kind of look up Munida Transect, that's data that you can download and start getting an idea of some of the changes that we're seeing here in the Pacific. So we'll kick off with the talk. Now, throughout, I have picked out about 6 key concepts from the first lectures that I'm just going to bring up again. Besides that, it's going to be mostly new material. But what's the first one? Well, the first one is ocean acidification is happening. I think we are all here. We all know it's happening. And We also know that it's a direct result of an increased CO2 in the atmosphere. Now, this is the figure that I showed during the original presentation, where we can see atmospheric CO2 increasing, so these dark blue dots, and that's been measured directly at Mauna Loa and Hawaii since 1958. As that is happening, we can see an increase in the partial pressure of CO2 in seawater, or PCO2 in seawater. That's another way to consider the concentration of CO2 once it gets into the seawater. At the same time, that's driving down the pH, which we can see through measurements and through calculations. Now I want to go back to kind of some things that were brought up on the discussion board. And so just looking back at past carbon dioxide levels. And here we're going to just look at the last 800,000 years. And if you look up past CO2 levels on the web, you'll find that a lot of people just kind of cut the time off there. And it's not because there's not other relevant information past that, but there's a good reason that we often simplify our conversation. And that's because for this 800,000 years, we have really good ice core data, and we've had it for a while. So we really have known what those past atmospheric CO2 data are. But also when we're talking about what's going on, often we're really concerned about us as humans and the ecosystem around it. So we're interested in the world as it is today. And so if we look at these things, what we can see is over the last 800,000 years, we have this up and down of atmospheric CO2 level. And if we think about humans on top of that, I think the oldest Homo sapien fossils that they found are about 300,000 years old. But if we think about when a lot of our cultures were developed, when a lot of populations explosions we're really just looking at the last little tiny bit right here, where the world was kind of already in maybe a slightly higher compared to the depths CO2 levels. And the issue is that recently, or in the last couple of hundred years since the Industrial Revolution, we have just pumped so much CO2 into the atmosphere, those concentrations have just shot up. Now, the issue with this are twofold. One, huge increase, but two, that it's happening so quickly. Changes have happened in the past, but when they happen on slower scales, the natural processes in the ocean can adapt. And I think Chris Sabine in some of the next module is going to talk a little bit about what happens in the oceans to bring the seawater back into equilibrium. The issue we're having right now for ocean acidification is really the fact that it's happening so quickly. Now, when we think about it happening, the real challenge is to predict and prepare, because what we actually need to do to stop ocean acidification is cut CO2 emissions. And given that that's not happening, we need to be able to address it and prepare for it so that our society, our cultures, our economies can keep moving forward in a way that we hope will be beneficial to us, while also protecting the ecosystem. Now, although ocean acidification is a global issue, we also know that the impacts are local. So globally, it's crucial to reduce CO2 emissions. However, locally, there are things that you can do to understand ocean acidification in your region and develop methods to predict the future impacts, but develop appropriate interventions. And just as a little bit of a background for that, kind of the importance of the region, why we're all here today. So I want to think specifically about some of the challenges facing the Pacific. And now for this, I have shown this really nice figure, which is part of the Pacific Islands Vulnerability Assessment, which was prepared by SPREP a few years ago, and it's just freely available. So I recommend that you all look at it. And it just really did a good job of looking just at this region and thinking about what the changes will be. And in the original lectures, I actually used this as one of the examples. So I'm just going to point out two key predictions here. The first is that by 2050, or within 30 years, the entire region is expected to have an aragonite saturation state below 3.5. This is considered low to extremely marginal or very low for a healthy reef ecosystem to continue to build a reef. Now, in addition to the concerns just in and of itself, as the saturation state continues to decrease, it's going to leave reefs more susceptible to other pressures, such as coral. Sorry, a little bit faster, such as coral bleaching. So next slide. One key thing to remember is that while this is all very concerning, there are things that can be done, and that's why we're here. So I don't think that we all signed up for this course because we wanted to watch our ecosystem's demise. Instead, we actually want to understand enough to do something about it. And actually, the single biggest misconception I hear when I speak to the public about ocean acidification is that because it's due to atmospheric CO2, there's nothing that we can do until we cut CO2 emissions. And that's absolutely not true. So just to get you starting to think about what can be done in your region as you're going through this whole module, I've listed just a few of the things here. Now, the top one, which of course I'm excited about as a chemist, is to establish a monitoring program. Now, a monitoring program is crucial to understand the current seawater conditions in your area. If you want to know what's going to happen in the future, you need to know what's happening right now. Once you have some local data, you can actually use that to predict what will happen to the seawater in the future. You can do that in very complex ways, or you can do it in simple ways. And certainly the amount of uncertainty is going to be very different in those two approaches, but there are a lot of resources out there to help you make those predictions. I am sorry, I'm going to have to pause for just a moment. My hearing aid's disconnected from the system, and I've got to fix it before I can go on. It'll just take me about 10 seconds.
Thank you, Christina. Thank you for putting that question in the chat, Denise.
Okay.
We'll also pop it into the Q&A as well, and that's something that we can address at the end.
Okay, and I'm back. Oh, sorry. Go ahead.
I was just going to also note that you may also use the chat to ask general questions about the course. We've got a number of the kind of course facilitators here. So both questions for Dr. McGraw on the topic, but also if you have questions about the OTGA platform, please feel free to also put that in the Q&A in the chat.
Yes, thank you. Right. Back to you, Christina.
Great. Sorry for that interruption. I forgot if nobody else makes a sound, they disconnect after about 15 minutes. So maybe one of you guys can speak up occasionally, or we'll just do this every 15 minutes. Anyway, here we are. We are trying to address ocean acidification. We've got a few ways to do it. Another thing you can do is just identify areas of increased risk and resiliency. Once you start putting together all of this information, realistically, most regions aren't going to have the public interest and the resources to protect all areas. So in your region, what are the areas that are going to be naturally more resilient? What are the areas most at risk? And it doesn't necessarily mean you protect one over the other, but that's the kind of information that's going to help you deal with ocean acidification in the future. Now for this one, I actually kind of combined two concepts in one. One, we want to inform policy. I think all of us who do research hope that that research is going to be used to make a difference. And so one effective way to inform policy, if you're making measurements or if you're doing kind of culture type experiments, is to study organisms on local organisms and local impacts under local conditions so that you can do a good job of kind of conveying to your community and to the policymakers and to the stakeholders what the impacts are expected to be in your region. Now, if your skill set is out of the lab, other things you can do are start identifying policies that can be used to address ocean acidification. There will be some regional policies, perhaps some national policies, but also some international agreements that can be used. Similarly, you can look at regional resources. So for example, here in New Zealand, which is a well-resourced country, we still actually just have one central lab that does most of our ocean acidification measurements. So our DIC, our pH, and our alkalinity and our PCO2, almost all of the measurements made are made in one lab here at Otago, and samples are just sent in because that's really the most efficient way. So there are going to be resources around your region, and not everyone needs to duplicate it, but just by identifying what's available, you can be a little bit more efficient in the work. And implement adaptation and mitigation approaches, and we'll just talk about a few of those a little bit later, so I'll skip it now, but also start engaging with stakeholders and communities. And SPREP has a lot of good resources for this. So for example, a few years ago, they made some local language posters in a few different languages just to help communicate ocean acidification to local communities. And finally, I think the end goal for a lot of people is to develop an action plan, work with the policymakers and develop a plan for your region, for your country, just to specifically address ocean acidification. So whatever your interest is here today, please just keep in mind that there are definitely concrete things that we can do to move the whole region forward in addressing ocean acidification. And so what is our next key point? Well, we know that the absorption of CO2 is causing pH to decrease. However, this can actually be pretty tricky to communicate. So even if we go through the numbers and we kind of understand that pH is on the log scale based on the hydrogen ion concentration or activity, the numbers are actually quite small. So from that same vulnerability assessment, I put some numbers up for the Pacific region. And we can look here at the pH values. And we can see that the pH kind of in the 80s and 90s, sort of about 8.08. And what we are trying to communicate to the public is that we're actually really concerned about this change of 0.1 that's going to happen over 50 years, or maybe 0.2 or 0.3 that's happening over 100 years. Now, those numbers can be really small. I mean, if we think about COP26, what was everyone talking about? Limiting warming to 1.5 degrees. When we talk about atmospheric CO2, we talk about an increase from 290 to 420. Last week, there was a 2% decrease in the US stock market that made front page news in New Zealand. Those are all really quite large numbers when you're now talking about 0.02 differences here. So make sure yourself that when you're ready to start communicating ocean acidification and these pH changes, you can really communicate the significance of it by that good understanding of the log scale. And we know from how well you did on the quiz that most of you guys really have that down really well. Now, another related key concept is just making sure that you understand these reactions. So I'm not going to have you go through them all now, one, because I have so many other things I want to talk about, but hopefully really by the end of this module, you'll be able to start with CO2 and water, and you'll be able to get yourself through that whole equilibrium reaction, because that's really the key. And it's also a key to remember that, in fact, in the seawater conditions we're looking at, over 99% of the CO2 is going to just kind of go all the way through this reaction until we get to the bicarbonate. So we're really looking at how these two are changing in a lot of ocean acidification studies. And we do that using these types of figures. And there are a few different names for them. I just like to think about them as looking at how the fraction changes with our pH. So we can do is we can look at the pH on the scale here, on our X scale, and then we can look at the fraction that each component consists of. So if we had a really, really low pH, so a pH of 0.2, we could say that really 100% of it is going to exist as the combination of CO2 and carbonic acid. However, for us, we're working in seawater, so we're really interested probably more in this middle range right here. So I'm going to go to the next slide and just focus in on that, and really just want you to note that while we're looking at the seawater ranges, we're in this range where bicarbonate drops really quickly with increasing pH. Carbonate drops really quickly with decreasing pH. And so if we just draw some lines on this, we can say, if we consider maybe some past global mean averages of surface seawater pH, was it about 8.2? We could see for the seawater conditions I used for my calculations, maybe about 88% of it was in terms of bicarbonate and maybe 18% in carbonate. But if we go to kind of some end of the century predictions, closer to 7.8, we can see that actually we've just increased those bicarbonate concentrations maybe to about 94%, and we've decreased those carbonate concentrations to 4%. So we can see when we're thinking about this change of carbonate to bicarbonate, those changes are really quite big, and they can get a little bit hidden when we're talking just about pH. Now, this brings me to the first of the participant questions, and this was a really interesting one. And the question was, is it possible that hydrogen ions can be absorbed in some way to minimize their concentration in seawater? And for that, I'm actually going to really expand this question and even take it a little bit further than the original question. But first, a side note, because I'm a chemist, and I just want to take this as a teaching moment to introduce a new term. So in my module and in Chris's module, which is the next one, we're usually talking about hydrogen ions or protons. But actually, if we want to be technically correct, or more correct anyway, that proton or that hydrogen ion doesn't exist on its own. Once it's created, it's not just floating through seawater waiting for something else to react with. It's actually going to just bind to the nearest water molecule, and that's where we have this hydronium ion, so H3O+. So it's these hydronium ions that we're actually increasing the concentration of with ocean acidification. Now, even though technically we'll be talking about hydronium ions instead of protons, I want to now take it even further and say that actually it's not even the hydronium ions that we need to absorb. Let's look at that whole reaction. We know it's this 4-step equilibrium, and let's think about what else we can do in order to reduce the hydronium ion concentrations. And looking at it, one of the natural things is to actually focus on the CO2. We know that we're decreasing the pH by driving that CO2 in there. So what if instead we could start pulling that CO2 back out? What are some options for that? Now for this, I have taken a couple of tables from the Policymakers Handbook for Addressing the Impacts of Ocean Acidification. This has got some useful things in it, and it's one of the resources we'll talk about in the extra workshop next week. I want to take you through a few aspects of the table, but I do need to just kind of point out a few things about it first. In this, we're talking about marine resources in terms of assets. So we have finfish, they're an asset because they're a food source, but they're also really critical in the ecosystem because they connect trophic levels. We have our shellfish, which not only are they food, but they're filter feeders and they build reefs. We have our coral reefs, which we know and love, and they are also key to our ecosystems. Often when we're talking about ocean acidification, people forget about marine plants, but of course, marine plants play a really big part in protecting ecosystems and keeping a healthy and vibrant ecosystem. And then lastly, when we're talking about marine resources, we'll just talk about ecosystem services, anything really that has a cultural, economic, or ecological value. And of course it will, because almost half the population lives within 10 kilometers of the ocean. So to answer these questions, I want to think about back to that equation and what can we do to either reduce the hydronium ion concentrations or reduce the CO2 concentrations, because they will pretty much do the same thing. And for that, we can actually look at this table and we can see with mitigation approaches. So this is a way that we acknowledge that ocean acidification is happening and what can we do to reduce that impact. This table includes 4 aspects. So for here, we can see that we can simply reduce CO2 emissions. That would be great. I would love it if we could do it. Secondly, we could reduce other stressors, such as improving the water quality. Now, this would be really important because anything else that is a stressor on your ecosystem is making it harder for your ecosystem to adapt to ocean acidification. We can also, I'm going to skip over alkalinization for a little while and skip straight to aeration. So aeration is this idea where you can take some air or some air that has a CO2 scrubbed out of it, and you can bubble it into your seawater. If you're bubbling it into your seawater, what's happening is as those bubbles come up to the surface, they're pulling some of that CO2 with it. So it's actually effectively removing the CO2 from the surface and it's ejecting it back into the atmosphere. Now, the one that I saved for last is this one here, alkalinization or liming, which is really probably most directly related to the actual question. And there are a few different words or terms you might hear it referred to. It could be called enhanced weathering, ocean alkalinity enhancement. And what this refers to is this idea that if you have mineral compounds and you add them to seawater, it will shift the equilibrium back, shift the equilibrium to create more carbonate as the CO2 is consumed. Now, what you would do is you would actually take the mineral, you would crush it really finely. What this does, it gives you really tiny particles. You have a high surface area for a relatively small volume. And then you just kind of scatter it in your region. Now, it will drive that pH up. It will increase the carbonate concentration, but there are some also concerns with it. So when you throw the minerals in, it's not just going to be, let's say it was calcium carbonate, it's not going to just be calcium carbonate. There are going to be a lot of other minerals mixed into, so you're actually throwing in some micronutrients also. So it's a little bit unclear what the long-term consequences of that will be. Also, it can be very energetically expensive to harvest and crush that rock, but it is a really hot topic, and because it's viewed as a good potential solution, there's a lot of research into it. So I suspect you'll all be hearing more about it in the future. Now, while not directly related to alkalinization, which is probably the best answer for the original question, we do have some adaptation approaches, and I just want to mention them too. So here we've got 4 different examples of different adaptation approaches, everything from just having more marine protected areas. So if you have areas where you can reduce all of the stressors somewhat, the organisms will be able to better handle any additional stressors that do happen. You can take species that you know to be more resilient, and you can transplant them to an area. So here we've got translocation of species. We're going to come back to phytoremediation and just skip straight on to genetic engineering. You can also just do genetic engineering in order to help organisms essentially evolve perhaps a little bit faster than they would have naturally. But phytoremediation, just like ocean alkalinity enhancement, is something that we're hearing a lot about. And phytoremediation works by taking CO2 out of the seawater directly. And how do we do that? We've got a couple of examples again from the same handbook, and we're going to start with this figure on the right. This figure on the right is data from Florida, and in this region, they wanted to restore some seagrasses. Now, seagrasses, just through photosynthesis, will take up CO2. When they take up CO2, that's going to drive that pH back up again, which will increase the carbonate concentration. So this group got together, they got together industrial partners, farmers, businesses, governments, and they all worked together to tackle different stressors. So some of them limited their fertilizer intrusion into an area. There was a reduction in coal-fired power plants, which adds more acid to the water also. There was less fertilizer being put into the oceans, a whole lot of different things in addition to planting the seagrasses. So they tried to reduce the stressors. Then they put the seagrasses in, and what you can see is as that seagrass coverage, this green bars, increased, the pH is also slowly increasing with it. So we can see that this phytoremediation has been effective, especially when it was combined with these other changes that just reduce stressors overall. The other thing I want you to note from it, though, is that actually this is, look at this, is about a 35 year period. And look at the pH. I mean, it probably really took 25 years or so just to be able to determine that that pH really has been increasing. So that's something for you to think about while you're doing monitoring. When you're working in coastal systems, you can just have highly variable pH levels influenced by so many other things besides pH. So you might actually need quite a long-term monitoring program to start seeing some changes. Now, in the Pacific regions, there have been also a lot more mangrove restoration, which does a lot of the same functions. And also mangroves are great because they help protect from storms and things like that too. Now, if we kind of go back to one of those very first equations that I was showing, and now we're just going to take it a step further, just want to remind you that I know we already spoke about bicarbonate increasing and carbonate decreasing, but for those chemists in the audience, if we think about it in terms of a chemical equation, we do also need to remember that calcium carbonate is in equilibrium in seawater, so there are free calcium ions, there are free carbonate ions floating around. So that's what this reaction happens. One of your excess protons can react with a carbonate ion and producing more bicarbonate. So if we put that all together, kind of our key concept from module 1, another one to go with, actually has to do with saturation state. So we know that carbonate is decreasing. One really nice way to quantify this is with the saturation state. And we learned how the saturation state is kind of this concept that can be really relevant, especially if you're looking or concerned about organisms that are calcifying. And the thing to remember when we're talking about it, though, is our saturation state refers to chemical stability. So if we talk about a saturation state of something that's greater than 1, we would think that that mineral will be quite stable. And in fact, you might even have a little bit of precipitation. Although when it's close to 1, they'll be so slow, it will really be negligible. However, if your saturation state is less than 1, it means there's so little carbonate, or sometimes calcium, but not really in practical situations, so little carbonate in the seawater that that mineral is going to dissolve. Now, some organisms, if they're healthy otherwise, can just pump in a lot of extra energy and still continue to precipitate, but it gets a lot more challenging. And so while the number is kind of this magic number 1 when we're talking from a chemical standpoint, if we're talking about the biological impacts, we're organisms that are calcifying really, like in New Zealand, where we have a lot of cold water coralline algae, they're looking at saturation states that are greater than 2 to be able to grow well. When you're looking at warm water reefs, you really want saturation states greater than 3.3. Which brings us to our next participant question, which is, how do we determine calcium and carbonate for the calculation of saturation state? And why is it dependent on salinity, temperature, and pressure? First, before I can answer that, we do have to delve just a little bit deeper in this calculation right here. Now, I'm going to start by just talking about KSP. So KSP is our solubility product. Every ionic salt has a solubility product, and it's just as simply a function of the concentration of your ions, in this case, calcium and carbonate, that would be present at a certain temperature at equilibrium. And so that's how we kind of get this idea of how if a saturation state is less than 1, it's less than equilibrium. That means that your numerator, or your current concentrations, is less than your denominator, or what your equilibrium conditions would have been. And so if we think about it just from a saturation state perspective, let me just take it one more step and kind of thinking about it in terms of KSP too. And we'll start by thinking of carbonate first. In order to get carbonate, we need to start with one of our 4 main parameters. So we talked before, and Chris Sabine's going to go into much greater details. To understand ocean acidification, you need to measure 2 of pH, DIC, alkalinity, or PaCO2. If you have those 2, you can use some standard software and calculate carbonate. This could be C-carb, CO2 cis. There are a lot of things out there. It is important that you throw in the other parameters of interest: salinity, temperature, and nutrients. Now, calcium, that one is actually entirely based on salinity, because we know that there is a defined relationship, and I actually known as in quotes for a reason. So we believe that the calcium concentration is actually about 0.3 millimole per kilogram of seawater per unit of salinity. Now, since salinity is about 35, this gets us to our calcium concentration of approximately 10 millimole per kilogram of seawater in the ocean. So the software itself, so C-carb, CO2 cis, it will actually calculate calcium for you based on the salinity measurement. So what's the importance of this? A lot of people, it seems, maybe think about salinity as a secondary measurement, but especially if you're interested in saturation state, that's how you get your calcium. And you can see that your saturation state is proportional to calcium. And so it's really important to do that as well as you can. It's also important to note that actually this defined relationship, which between salinity and calcium, was defined in 1967, and it's a really good, nice relationship. There are a few areas of the world where it varies by as much as 5 or 20%. So if you think that could be a concern for you, you might want to actually measure calcium and just see what the relationship is in your region. Now, the next question was, how is this going to be dependent on salinity, temperature, and pressure? There are a few components to this answer. And so I'm going to start, though, just by showing this great figure that I took from a paper. There's a link right here. And what we're looking at, actually, we're looking kind of from Alaska down to Antarctica, you know, kind of in the Pacific region. And on this whole transect, we're actually looking how the saturation state changes with depth. So we can see near the tropical Pacific that the saturation state at the surface is, you know, reasonably high, 4-ish or so. It's definitely a bit lower in the cooler water of the Pacific, of the poles. But notice that as you go deeper and deeper, it gets quite low. It gets actually, in fact, well under saturated value. So why this change? There are, I guess, 2 big reasons. One thing I want you to know is that anything that's driven that has a change in the carbonate concentration will actually drive a lot of that change. So these changes we're seeing from the equator to the poles, this is because carbonate is about 250 micromole per kilogram here, but closer to about 100 once you get closer to the poles. So that factor of 2.5 of carbonate concentration is going to be a factor of 2.5 in saturation state. Now, when we think about the temperature sensitivity, we actually know that the equilibrium between bicarbonate and carbonate is highly temperature dependent. That's why it's so important that you make a good temperature measurement each time you make these measurements. Now, so while we can say that the carbonate concentration is dependent on temperature, but actually the KSP is also dependent on temperature, but actually not very much. It's a little bit temperature sensitive. It's actually much more sensitive salinity. And of course, our calcium is also sensitive salinity. I would say one of the more interesting parts to think about is pressure. And so that's why I put the pressure figure up here. Now, pressure is another way to say depth because the pressure of the seawater is going to increase by about 100 bar for every kilometer we are below the surface. So these changes here, we can ask ourselves, what are the causes from them? And there are a few of them. One of the big ones is that our carbonate concentration will decrease with depth. And this is because the temperature is going to get colder as you go deeper. You're going to have circulation processes that are bringing different seawater masses of different seawater age in, but also there's going to be a release of CO2 due to biological respiration. That CO2 release is going to decrease the carbonate. Now, technically, because of the pressure, the equilibrium constants that determine whether or not you're in the form of bicarbonate or carbonate will also change, but they change by such a small amount that they're almost negligible. And so the final one is the KSP component. So we can see how carbonate changes, but KSP also changes, and it actually changes quite a bit. The difference between the surface KSP and the KSP 10 kilometers below the ocean is a factor of 2. So it gets about 10%, it gets twice as high when you're 10 kilometers below the ocean. So we put this all together, we can see that the saturation state will decrease at depth because the carbonate concentration on our numerator gets a lot smaller, but our KSP doubles, so it gets bigger. So it's kind of a 2-factor change that we're seeing going on. So let's just go back to the beginning and consider again our chemistry of seawater. And we can say that our changes are straightforward. We know CO2 is increasing, we know we can measure it, and we know we can predict it. So this is actually a really good time to consider our next participant question, which is, what is fugacity? Now, there are a lot of different ways to define it, and you often hear it called effective pressure or real, in quotes, partial pressure. Sometimes the tendency of gas to escape from seawater, or corrected partial pressure. Personally, I find this last definition, corrected partial pressure, the easiest to consider and conceptualize for myself. So to do that, we actually have to start from partial pressure. So partial pressure, or CO2, is calculated from the mole fraction of the gas times the total pressure. So assuming that the total pressure stays constant, the partial pressure of CO2 will increase as the mole fraction increases. But when and that's kind of what we're seeing right here. But when we consider partial pressure, we're actually saying or assuming that all gases are ideal. So for those who have taken chemistry, the behaviors of an ideal gas, there are about 4 key ones, but they're essentially that all particles are the same, they move randomly, when they collide, no energy is lost. But importantly, we assume that there are no molecular interactions. So one molecule in your gas will not be attracted or repulsed by another one. Now, if you have a sufficiently dilute gas, it actually behaves like an ideal gas, and that is just fine. We use fugacity when that's not the case, and that would not be the case in seawater. So for fugacity, we start to consider non-ideal behavior. And so that means we acknowledge that our molecules will have some attractive and repulsive forces. How do we actually calculate it? Well, I guess this is the key. You do calculate, you don't measure fugacity. You actually calculate it from the mole fraction of CO2, but then you add in some additional terms into the final calculation to take care of molecular interactions and anything else that might be in the gas phase. Now, if you were to do it, you would presumably be using some of the software we spoke about, so C-carb or CO2sys. These actually do those calculations for you. So even if you put in CO2, it actually converts it to fugacity and then does all of the measurements. If you want to learn more about fugacity, the 2007 best practice guide for ocean CO2 measurements, which I have a link in the original talks, is really good. It explains it very well, but it also takes you step by step through the calculations if ever you want to do it by hand. And so moving on to the next one, I didn't mention it as a key point, but it really is. It's just really reminding you that while we can actually do a pretty good job of predicting the changes in seawater chemistry, predicting the changes to our marine assets, so to our fish, our reefs, whether they're shellfish or mangroves, and our resources is a lot more challenging. And this is where really all of the different groups around the world doing their research really contribute to be able to do these big meta-analyses where they take everyone's research all together and try and consider it together. And so again, I just want to direct you back to that Donny paper if you need a reminder about how we think ocean acidification is going to affect a lot of different organisms. And so I just want to take kind of a side and just talk about one organism. And I just want to remind you now about Sam DuPont's research. It's one of them that we had talked about. And it was, can you taste ocean acidification? And just showed that he had grown these shrimp, which are well loved by Swedish people in current and ocean acidification conditions. And then had people taste them, just people off the street. And what they found is that the ones grown under future conditions did not taste nearly as good in the view of the public, and that really got them engaged. So we're going to take a quick pause here. Alexis, you happy to share that video?
Yes, absolutely. And I also want to point out that we've had a couple of questions come in that we can certainly save time at the end to address, or you might weave the answers in through your next few slides. A lot of them relate to sort of remediation, phytoremediation, and resilience. So maybe while the video is playing, Christina, you can take a look at the chat and the Q&A box. Great. So why don't I pull up this video that Christina is sharing with us today. And Sam DuPont is actually one of the lecturers later on in this course, so you will hear from him directly. But for now, here is a preview of some of the work that he is doing.
Most of the stressors that we are studying in the lab, like temperature, oxygen, or pH, all relates to the same thing, which is carbon dioxide. We know that we produce more and more carbon dioxide every year. And if you want to fix these problems, what we need to do is mitigate, decrease carbon dioxide emissions. And we also know that it's going to be a really challenging task as we need to reach large-scale collective action, meaning that we're going to have to work at the global scale on a wide range of stakeholders like kids, citizens, industries, or policymakers. And all these different people want different things. If you talk to a policymakers, they don't want more problems. What they want is solution. If you want to talk to a citizen, they want to know what's going to happen to things they care about. And most of the time, the science we do is producing like a lot of information, but that's not really relevant for this particular task. So it's not really driving the change we want in society. So we were arguing that if you want to be more efficient at reaching impact changes, what you need to do is develop science targeting this goal. And that's not what we do most of the time. So we need to move toward a science that is complicated and not really society relevant, to something that is really targeting what people care about, emotions, and have a science that is clear and simple enough. And if you reach this, then you can drive impacts. One example is something we did in my lab, where we decided to go into the street and ask people in Sweden what they care about. And one thing they really care about is seafood, and in particular one species of shrimp, the northern shrimp. If you go in every restaurant in Sweden, you're going to have the shrimp sandwich, and this shrimp sandwich is really popular. Everybody loves it. Everybody remember the first time they tried it. And so if you really can show that there will be an impact on this shrimp due to global warming, ocean acidification, or the oxygenation, then you will really have an impact potentially. So we tried that. We collected shrimps in the field, we exposed them to different pH, simulating ocean acidification, and we could see that people could actually taste the difference. And because of that, that was a fantastic communication opportunity, and we had a lot of impact in the press, on web, and so on. But even better, we could show that if the people experience physically ocean acidification instead of just hearing about it, so they had an emotional connection with the stress, what happens is that they are more willing to change. So if you want to be efficient at driving impact in society, you have to think about three things. First, who am I talking to and what do they want? You have to understand the culture of your audience. 2, what is my goal? What do I want to achieve? Do I want to make them change, and so on? And when you have these 2 pieces of information, what is the most optimal method to reach my goal? Good luck.
Thanks, Alexis, for sharing that. I think I wanted to show that, one, it's a really nice introduction to Sam, who's going to be a really useful resource for you when you get a little bit further on in the modules, but also just as a chance to start thinking now about how the work you're going to do, how you can best and most effectively communicate, because it can be really one of the best ways to make sure that whatever you're doing, whether it's monitoring or research, ends up being discussed out there. So I did have a look at those questions, so that's really good. I'm sorry if you were trying to interrupt me. I didn't come up in my audio at all. Meredith had some good resources there, and I would really agree with what she had said about it. And I would say for some of the other questions that we don't get to, maybe for the panelist team too, we could just translate those ourselves to the discussion board and talk more about them there, because I think that's really a key, and it's really nice to see everyone thinking about it. Kind of, what are you going to do? What's your long-term goal with doing this research? And so with
Thanks
that,
so much,
actually,
Christina. I wasn't
yeah.
interrupting you. I want to let you roll. I also will say that all of these questions, I think your depth of understanding is going to increase with every module. And so keep these questions, keep thinking about them throughout each module as you learn more about ocean acidification.
Yeah, I would completely agree. And so it's just so exciting, actually. I'm so excited about the program in general, because you're going to learn so much about so many of the different aspects. And in some ways, probably coming back to this first module at the end, you'd be able to get so much more out of it also. But with that, this is the last question that people ask, and that is, what is natural variability? Because I mentioned that, I think, in the second or third talk. And then how does it affect the measurement of the parameters? And so with this, I would just we'll just have a little pretty picture to look at, because in lots of ways, I think thinking about natural variability in terms of something specific is very useful. So here we have some kelp. So you can think about a kelp forest, and we've already talked about how a lot of the marine plants take up CO2. So with photosynthesis, the kelp forests are going to take up CO2, they're going to respire, they're going to put it back out again. What you can see, if you look at a daily cycle, is you can see an up and down and an up and down of the pH within that kelp forest, as the CO2 is taken up and then respired back down again. So we can think, if we're just thinking, I mean, let's just say a 3 by 3 meter patch, you could imagine that the pH within that little bit of kelp is going to change dramatically. So when we start talking about natural variability, we're talking about any kind of process that's going to shift the pH or their carbonate parameters that are different from the CO2 coming in from the atmosphere, or maybe anything acidic coming in as runoff, or low pH coming in as runoff. And so what will change it could be a whole range of biological, chemical, and physical parameters. It, for example, light and temperature will make a difference. We see that our equilibrium reactions, they're very temperature dependent, but also just mixing of different seawaters. And so if we actually just go, these are some figures that I showed in one of the previous ones, but now that we've kind of talked a little bit more about the background information, we can see some of the natural variability on very different scales. So if we look just at latitudinal processes, we can see that the pH actually varies with season, and it's going to be high or low depending on whether it's winter or summer, wherever you are. And so what's the cause of that? Well, a lot of it's going to just be differences in things like irradiance and temperature. Those are going to drive primary productivity, and primary productivity, that's going to have phytoplankton blooms, and that's going to change the pH of the seawater. Now, if we look at slightly smaller scale events, and these are kind of regional scale processes, so actually looking at a particular phytoplankton bloom, we can see that the pH can go up and down. So in this particular case, actually, we're looking at the phytoplankton blooms is the green line. So that's going to happen over the course of about 5 weeks. So we can see CO2 being taken up. And then also we're looking at a process of upwelling. So we're looking at low pH water being brought up from deep water to the surface. So those are both natural processes, and they're going to drive carbonate concentration change. Now, at the same time, we could just have things like I was talking about before, like maybe in a kelp forest, anything that's going to change the pH due to photosynthesis and respiration. Now, if we put all of those together, what we need to consider is that over time, if you're doing monitoring, because that's really, I suppose, the second part of the question that the people asked, is that if you're in a region and you're having noticeable enough pH decrease, you're going to see that pH decreasing over time. But if at the same time you have these natural processes that introduce a lot of variability, which if you're on the coast is really reasonable, you don't see it nearly as much in the ocean open, but sure, your pH is going to be slowly going down. But boy, that pH also just might be going up and down quite a bit due to daily cycles, maybe due to seasonal cycles. So if you're doing monitoring, it's something you need to keep in mind. And there's no kind of one solution besides acknowledging that you want to capture that natural variability so that you understand it, so it can become part of your understanding of your long-term monitoring program. So it kind of goes back to this idea that when you're doing monitoring, you need to make sure to do it long enough to capture these changes, because doing it any 2 points in time, you really won't know what's happening with ocean acidification. Now, the last point, I know it's kind of redundant at this point, but I wanted to put it in again. I think it ties in nicely with Chris's next module, just how important it is to actually make these measurements. So you've got to make 2 of the 4 measurements. Only looking at pH isn't going to really do you any good. Make sure that you're capturing that complete carbonate system. That'll also let you do things like calculate saturation state. And so I'm just going to wrap up with this here. I would like you to be reminded of an extra workshop that we're having next week. And it's going to be kind of led by SPC. And so Katie Salapi at SPC is the lead of the new Pacific Islands Ocean Acidification Center. But then there's a group of 4 of us who've gotten together and we've just been brainstorming and thinking about what resources we think are the most useful for people in the Pacific. And of course, I know that not all of you are from the Pacific, but actually be useful for you too, but a lot of them obviously are more useful for people in the Pacific. Now, if you have a chance, and I'm actually going to stop sharing now because I would like to just share a link with you. I would really love it if you could, if you're interested, sign up for the OA Information Exchange. Now, you don't necessarily need to register if you're not interested in it, but it would be really great if you went and visited it. And this is because this is kind of a platform run by NOAA, and it's a really good way to share information on ocean acidification. So have a look at it. If you think it's useful for you, go ahead and register. Consider signing up for the Pacific Island Hub. And if you're interested in monitoring with the Go On in the Box kit, you might want to sign up for the Go On in a Box Hub. And we're going to go through it as one of the resources. And so with that, thank you all for showing up for yet another hour of listening to me talk about my love of ocean acidification science. And please keep adding questions to the discussion board because we'll keep answering them.
Yes, absolutely. So we've tried to provide some kind of live chat to everyone to answer some of your questions. And really, truly, I think over the course of the modules, you will find out that some of these questions are pretty hard to answer and we don't necessarily have answers, but that's part of what the community is trying to do right now. And you'll get a better sense of how you might help us answer those questions even. The OAIE, the way I think of it is it's sort of the permanent discussion forum for the OA community. So the one on the course is kind of a safe space as you're learning. It's a great place to really dig into the course materials, but then the OA Info Exchange is there forever for the whole community to come together and engage. So I want to thank Christina so much for her time. I also want to give Caitlin a moment to share any announcements related to kind of when the quizzes close and next modules and anything like that. So Caitlin?
Thank you so much, Alexis. I'll share a reminder after this call, but just the next quiz closes on this Sunday, or I believe in Fiji, it's a little extra time. So Monday morning is your last chance to complete the quiz for Module 1, as well as the pre-course survey. I'll go ahead and send out another email this weekend with more information on what's going on next week, including the great session that Christina's helped organize, as well as our regularly scheduled live Q&A. Next week will be with Dr. Chris Sabine.
Thank you all so much.
Thank you.